Hello everyone, welcome to this amazing new venue that we have Man AHL to thank. So everything is basically the same format as usual. The only thing I need to tell you is that there are no fire drills scheduled for today. If the alarm goes off, then we just go out the same doors that we came in on. We'll have community announcements after the first talk, as per usual, and a short break, and then the second talk, which is Marta Garnella. First talk is Simon Knowles, who is the co-founder and CTO of GraphCore. He's going to be talking about computer evolution in the context of machine intelligence.
Thanks, Martin, and thanks, Dirk, as well, for the invitation to this, I must say, quite posh venue. Thank you all as well for giving up an hour or so of your Monday evening. I'm going to get into trouble soon, I think, for not delivering a sort of deep tech denouement of GraphCore's technology. I'm not going to do that today. I'm going to try and give you some context of the world that we're launching our company into. But the deep tech denouement will have to wait for another day. I think we live in interesting times. You've probably heard various people make these sorts of claims in various ways, but to me, the harnessing of machine intelligence, or the mechanization of intelligence, is the biggest tech transition we've ever seen. We don't know how long it's going to take. Could take 100 years, could take 1,000 years. But it's probably bigger than the harnessing of machine power 250 odd years ago. And we are roughly at the level of awareness of it that Watt and Trevithick and Stevenson were when they first built a steam engine and amazed themselves because it had the power of 2 horses. And of course they couldn't envisage jet aeroplanes and holidays in the sun that we now take for granted. And in the same way, we cannot envisage where this goes. So I'm not going to dwell too much on that because that's philosophy. But as a computer designer, what I can say is I've never seen, in 35 years of building chips for various forms of processing, I've never seen a better reason or a bigger reason to re-examine the whole way that we do computing. Intelligence is a completely new type of workload. It involves new types of data structure, and it's going to be worth an absolute fortune when we master it. Those are all good reasons to re-examine what we have been doing for the last 70 odd years of electronic computing. Now, I can't see the future either, but I can have a stab based on experience of what's going to happen in the next few years, and that's mostly what I'm going to talk about. I think over the next longer period, tens of years, we'll reinvent pretty much everything. So there are 4 parts. At this stage, there are 4 interesting parts to the workload of computing intelligence. It all revolves around models, of course. And a model is 2 things. It's a distributed set of data structures, which are generally probability distributions, because what they are is digests of learned, interesting data. And then also embedded in the same structure is, if you like, a very highly parallel set of algorithms for processing on that data structure. And the 2 are sort of co-embedded in graphical structures. So our new data structure is actually the graph, the mathematical graph. Very large. Here is one from our tool chain, actually, for ResNet 50. You've probably not seen, those of you familiar with ResNets, you've probably not seen them drawn like this. Our tools fragment ResNet 50 into about 1 million nodes. This is a rendering of 1 million nodes, and obviously you can't see the nodes, they're too small. But you can see clusters of them, and you can see umbilicals of connectivity between them. But the important thing is that what happens at the nodes is generally tensor arithmetic. And everyone's very excited about tensor arithmetic at this stage of the evolution of computer intelligence. And NVIDIA, of course, they launch tensor cores, and we have TensorFlow, and Google have tensor processing units, etc. It's all about tensors. I'm not that excited about tensors. I mean, it's the very atomic level of what goes on. It's just a higher dimensional form of linear algebra that's well practiced. For a long time, we built DSP chips and image processing chips that use slightly lower dimensional linear algebra. Now we're going to build things that use slightly higher dimensional linear algebra. That's not very exciting. What's very exciting is the graph. As I will explain, I think we're transitioning from a sort of tensor-focused viewpoint to a graph-focused viewpoint of this whole compute job. The 4 kinds of compute I mentioned, really the one that we've mostly concentrated on is learning a model from data. It's just an optimization, a very clever, non-convex optimization in which we try to generalize characteristics of the data without learning the data on structures that are quite capable of learning the data. So it's a very interesting new space. But that's one of 4. Obviously, model discovery. In other words, rather than engineering the model you're trying to learn the data with, you try and discover it. This is a recent field of significant activity. And as you can imagine, each time you discover or try out a new model, you have to learn that. So exploring model structure tends to amplify the amount of compute you've got to do by a factor of another few hundred or thousand or million. Often the models need to interact with environments. Reinforcement learning for driving cars, obviously, better practice not running over pedestrians in a simulator than on the road. So part of the compute workload is environment simulators, and these things can be every bit as complex as the machine intelligence agent. And then, of course, having learned these things, they're used in inference applications without adaptation for language translation or whatever. Tends to be much more focused today on discovery and learning than on deployment. I think that's just because we're at the beginning and we don't really know how to do it yet. In the end, it will all be about deployment. As a computer designer or as a processor chip designer, I can tell you one thing. Processors are built, generations of processors are built whenever a sufficiently important new type of workload emerges. This is one. I can guarantee that whatever we end up using for machine intelligence will not be something that's already on the shelf. We won't be using Intel Xeons. We won't be using GPUs, in my view. My old friend Jensen would disagree, obviously. We've called our new thing, the graph processor, an IPU for Intelligence Processing Unit. I would have liked to call it a graph processing unit, but GPU's already taken. I don't really care what you call it. Obviously, Google have their tensor processing unit. Other people will have other things. But what I am completely certain about is that new types of processor architecture will be born for this purpose. So where are we in the search for suitable compute platforms? Well, we are already building chips which are the biggest we know how to manufacture. Every fab in the world is limited by the same physics and actually the same optics and uses roughly the same equipment. It can make a chip of roughly the same size. About 825 square millimeters is the biggest chip of any type that anyone can make. So we're already there. The NVIDIA Volta is that big, roughly. Our Colossus machine is roughly that big. We're power limited at the chip. We cannot extract more heat from the chip. We cannot really feed more amps into the chip. These chips are often running at a couple of hundred watts at a power supply that's well below a volt. So the current being passed through tiny little metal conductors on the PCBs is greater than the current that goes through the starter motor cable of your car when you fire it up in the morning. It's absolutely huge and increasingly difficult to deal with anymore. So we're completely power limited. We have over-focused on matrix products. I will show you that shortly. We're just learning to do 2 things. We've got to the point where for small inference jobs in the cloud, the chips are now too big, too powerful. So we have to learn how to do multiple jobs on one chip. And those multiple jobs may come from different people. And there may be security issues involved in them not interfering with each other. So we're learning how to do that. For training, we've now got to the point where actually one chip often takes weeks or months to do an interesting job, so we would all like to apply tens or hundreds or thousands or hundreds of thousands of chips to one particular training job, and that's really hard. And then finally, as I said, we are transitioning from a tensor viewpoint of the data structure and compute load to a more of a non-homogeneous graph viewpoint. Proof that we've over-concentrated on matrix products. So you might go out and buy a Volta GPU. It has a headline performance of 125 teraflops. You use it to train a popular neural network. You always use ResNet 50. I know it's quite quaint now, but everyone uses ResNet 50, so here you go. You get about 11% of those flops. If you look at how Volta does on most of the Baidu deep bench, test bench, for RNNs, you'll often see that you get 1% of the headline flops. So if you like, we've put lots of effort into improving dot products, matrix, multiply, that sort of thing. And we've done such a good job at that it's not about that anymore. It's about all the other stuff. And this, if you like, is evidence number one for the assertion that we're moving beyond the tensor as the interesting task and to the graph as the interesting task. I've put Colossus up here. We haven't actually declared what Colossus's performance is yet, but it will be at least 200 teraflops. We obviously know what it is, but we just haven't announced it yet. I have put TPU2 up, but I should say Jeff Dean did reveal at Scaled ML a few weeks ago some slightly better numbers for TPU2. He didn't say what the batch size was, so I've left the known batch size case. I'll come back to batch size, because you notice that Colossus achieved this level of performance with a very small batch. That's not really the point of this foil. The point of this foil is to prove that we all get low utilization. And I've put us up there to say that we do as well. So this is not NVIDIA bashing, it's not Google bashing. We just all have over-concentrated on one thing. An interesting question you could ask is, will it all be about neural networks in 5 years' time or 10 years' time? 5 years ago, it wasn't. It was all about decision forests. 5 years before that, it was all about support vector machines, and etc. So it might be all about neural networks, but I would say that our understanding of what we need to do is nascent, at least. And there are some things that we can now rely on. So we know that what we're trying to do is produce models of the interesting characteristics of data. The data is intrinsically noisy. In other words, we have samples of a distribution. So our learning is stochastic, and what we're learning is probability distributions. That's a sort of general statement. The probability distributions are very high dimensional as far as we can tell. They're also very highly parameterized, usually many more parameters than the number of samples that we use to train, which means, in principle, they can just memorize the data. And we apply a lot of effort trying to make sure that they don't memorize the data, but they generalize. Fashions in terms of models and algorithms change every year. And we are at I would say, the capability phase of this new market. We're all trying to work out how to do it. And for some companies, this is an existential point. Facebook have made an enormous business, possibly on espionage, but I won't go into that. They've made an enormous business on the basis of trying to understand or interpreting largely text data to work out what adverts to bomb you with. And the more people go to other forms of media, like video, obviously the more they need to try and understand what's going on in a video. And I don't just mean recognizing what's in the video, I mean actually understanding what's happening in the video. Otherwise they won't understand the nature of chat between people. And that means they won't bomb the right adverts, and that means their business collapses. Likewise, Chrysler, they need to learn how to drive a car at least as quickly as BMW. Otherwise, their business collapses. So this is existential for huge businesses, extant businesses, as well as obviously being a basis for forming completely new businesses in new applications. And at the moment, everyone is focused on capability. How do I do X? And all of our customers, I can tell you, tell us, we don't care what it costs. We don't care how much power it consumes. We don't care even if we have to rewrite our software in some wacky language. We just need to get there before our competitors. And that's a really, really unusual situation. It's a very nice situation for a nascent company to grow up into. But we will, later on, become interested in efficiency. And then suddenly cost will matter, and power will matter, and conformity will matter, and everything else will matter, but we're not there yet. So, what do we need to build now? I think, to be honest, we're going to be in this capability mode probably for another few years. So we're building machines now, really, for capability, for discovery. It's odd just to think that there is a market that's big enough that you could actually design a really, really expensive chip, biggest chip you can make, most sophisticated, most expensive chip you can make, and you're designing it for research. I don't think that's ever happened before. And that's a sign of how important this market potentially is. So until we know much more, we need machines which certainly exploit massive parallelism. Talk a little bit about that. Are agnostic to model structure, because we don't know whether neural networks are it in 5 years' time. We can assume various things. They're very high dimensional, so they must be sparse. In fact, when we embed them in low-dimensional memories with few addresses, then we must induce more sparsity. So there's a lot of sparsity around, and we can exploit that in our machine structure. We also know that the world has invariances. Vision has translational, rotational, etc., scaling invariances, and we can exploit those, and that's what CNNs do. Likewise, sound and sentences and things like that have invariances in terms of time. And recurrent nets, it's just convolution in time instead of in space. So we exploit those. They must have a simple programming abstraction, because we're in a race, and nobody wants to spend a lot of time fiddling with complex programming. They need to spend all their time working out how to do their job. And I think probably at this point, there's no point building chips that just do inference or just do training, or even are just for research as opposed to industrial application. Just build a chip that does everything. So suppose we want about 1,000 times the machine intelligence compute. I ask everyone how much more compute they need. Usually they say 100 times or 1,000 times. One chap did say infinity. He was probably exaggerating, but not by much. How much are we going to get for free from silicon scaling? We're all used to living in a world of Moore's law. That actually stopped a while ago. Some of you may have noticed. Stopped around about 2005, in fact. It wasn't Moore's law that stopped. It was a different thing called Dennard scaling. And as a consequence of that, all processors, all throughput machines, all maximum size machines are now power limited. Now what that means, this is my crude graphic, most of the power in a chip is burned in moving stuff along wires. Not much of it's burned in transistors. Some of it's burned in leakage, but again, not much. So holding stuff, holding state, burns a little bit of power, but not much. Most of it's transport. The wires, well, these are roughly to scale. The wires are about twice as tall as they are wide. They're generally arranged in X-Y alternation. A modern process will have about 13 to 15 layers of wires to connect the transistors together. And imagine you're one of those wires in the middle of that. Pretty much all of your capacitance is two other wires. And what happens as you shrink these structures, which we do each time we go through a process node scaling, is that capacitance goes up per square millimeter. What happens is we get more stuff in a square millimeter. A process node scaling is typically a root 2 scaling in linear dimension. So one node gives you roughly twice as much stuff per unit area, where stuff is crossing points of wires, and we manage to build the transistors to the same density. So it's transistors. And if you do that, you get 2x the transistors per square millimeter. What happens is your capacitance density goes up by about root 2. Now power is given by that simple little equation there with a constant multiplier, CV squared F. V is the supply voltage. What we used to do is just bring V down by enough But it not only allowed C to go up, as it naturally does, but it also allowed us to take F, the frequency, up. You've probably all noticed that your laptop doesn't run any faster than it used to 10 years ago. That's because we can't do that anymore. We don't have any spare. So frequency tends to be the same. We're now at the point where actually we can't bring the voltage down very much further either, without either changing electrons as our charge transport mechanism, which is quite a biggie for silicon chips, or changing the silicon band gap as our transport medium, which is also quite a biggie for silicon chips. That one has possible solutions in quantum wells and carbon nanotubes, but not for the next 10 years, probably. So we're kind of stuck with this for now. So if we could reduce the voltage by about 20% because of that square factor, we could keep the power per unit area the same, and then we just get twice as many transistors. So you get twice the performance in the same power at the same speed. Unfortunately, we can't reduce the voltage by 20% anymore. This is roughly what happens. So this is how Xeons, Intel Xeons, I like to study these because a Xeon is built to do basically the same thing, generation after generation. They tweak it, but it does roughly the same job. So you can compare nicely what the effect of scaling is in silicon by looking at Intel Xeon processors. And they are tracking roughly the constant voltage scenario. In other words, they get about twice as many transistors per generation. So you get twice the number of cores, usually. But unfortunately, the power density is going up by this root 2 factor. And what that means is that you don't get twice the performance, you get root 2 the performance to balance those two out. So about root 2 the performance. What that means is if your chip's entirely full of logic, as things like Xeons and GPUs tend to be today, the amount of chip area that you can actually power at any time is going down. We are roughly, with today's generation of chips, the pink box on the left. You already can't power you can't power all of your die. Maybe you can power half of it, maybe a little bit more. A reticle sized die, a maximum sized die, 800 square millimeters or thereabouts. But as we go forward to the next process generation, the amount of die that you can power is going to fall, and the one after that is going to fall again. So what's the point in building big chips? You can't turn it all on. You can't use it. Obviously, you could turn the frequency down, then you could use it all, but what would be the point of that? You should have just built a smaller chip. It would cost less money. The answer is memory, and we'll come to that. So silicon scaling is going to yield probably 3x in 10 years, probably. I mean, if we could fix the voltage scaling thing, you'd get 10x, but personally, I don't see a way of doing that today. So you're going to get about 3x. So if you want the 1000x, then you're going to have to, or 100x, you're going to have to do other stuff. And the other stuff that you can do, there are really two options today. One is completely rethink the way in which you build processors, obviously. You have to do that. And the other thing is bolt chips together in such a way that you can pretend that you've got a bigger chip with a bigger power budget. Obviously, you're still going to burn more power, and at a system level, that might cause you trouble, but at least at a silicon level, at a chip level, that's a solution. And I would say, I mean, I've, in my career, been through 8 generations of processor architecture for various different workloads. All of them from scratch. It was all built for a new workload that emerged. And every single time, if you didn't get the software thinking to adapt at the same speed and the same time as the hardware thinking, then you were wasting your time. We did do that once as an experiment, and we did waste our time. We thought we'll just change the hardware, and then the software world will work out that it's really brilliant and it'll catch up. Only they didn't, because they didn't have enough forewarning. So rethinking hardware on its own is a waste of time. You have to rethink programming methods. In this new world of the new application, we're also going to have to think very carefully about our algorithms. A lot of what we do in terms of model structure and learning algorithms today is predicated on the presumption that we're going to use GPUs. And GPUs have a particular set of characteristics. The best platform you can use today, probably. But actually, for the long term, probably not the right set of characteristics. So co-adaptation is essential. What's going to drive new architectural thinking for machinery? Well, power limit is the main thing. So silicon efficiency is now the ability to use all the power you've got as well as you can. The productive use of available power. If you ever get to the point where your machine is not using all of the power, then it's wasting performance. So we try to build chips to use power now. Memory, if you put memory on chip, it consumes very little power relative to logic. So memory is the obvious thing to start filling the die with, now that we can no longer put very much active logic down. There's a central theme of what GraphCore set about doing, and I'll explain a bit more about that as we go along. I've said transporting data, moving data about, is very energy expensive. So try to keep your data local. What does that mean? That means distribute the memory all over the chip. Don't put a big pool of memory in one place and a big pool of processing resources in another place. Scatter them about. Distributed machine. Serialize communication and compute. That's a really weird thing to say to most computer designers because they spend much of their time trying to work out how to overlap them, because that used to be what we called efficient. But in a power-limited scenario, it is no longer efficient, and I can explain that shortly. Cluster multiple chips to pretend you have a bigger power budget. That's obviously something. The other thing you need to know about silicon is a thing called Pollock's law. It's not, well, Pollock's rule. It's not a law. It's just a practical observation over many, many years. And that is that there's a fairly poor return, something like a square root return on the complexity of a single processor. If you throw 4 times as much transistors at trying to get your processor to have high performance for a program running, you might get 2x the performance, roughly square root. So if you're interested in throughput, the wrong thing to do is to put down a few complicated high-performance processors. The right thing to do is to put down lots of really simple ones, and then you'll get aggregate performance higher. And then, to be friendly to software, there are 2 things that we need to recognize. One is that actually writing a parallel program is quite hard. Many of you may have tried writing a parallel program for a sort of quad ARM core in a mobile phone. That's quite hard when there are 4 cores. But we're talking about machines with thousands of cores and in future millions of cores. You will never be able to write that yourself, obviously. You'll have to write tools that do that mapping for you. What that means is you're going to need a really simple abstraction of parallelism, and that abstraction should be safe. Because if that abstraction is capable of producing concurrency hazards, like races or deadlocks or live locks, then it's going to be a nightmare. So we need a really simple abstraction for the mapping of parallel programs, very highly parallel programs, to very highly parallel machines. And the other thing is that that mapping, at least for random graphs, is NP hard. There are 3 parts to it. One is allocation of work across different processors. The second is the allocation of memory, the division of memory across distributed memory on different processors. And the third is the scheduling of communication. Each of those is potentially NP hard. So you don't want to be doing that in real time. You want to be doing that when you compile the program. Now what this means is that the patterns of communication need to be known at compile time, and the performance of the machine ideally should be deterministic for those patterns so that the compiler can predict it. That's the same as saying that your graph structure should be fixed when you compile. So we don't like dynamic structure. Now this is not that big a deal. It's actually exactly analogous to not liking self-modifying code in a sequential world, where a compiler has to deal with a call graph that may change. It's also the same as what goes on in your head. Your axons and neurons do not rewire dynamically as you have different thoughts. You can, of course, build switching nodes, so you can emulate dynamic structure, but the thing that you compile to, the graph structure, must be fixed. And that's got to be a key characteristic of programming idioms. Right, this is the sort of machine I think we need. A pure distributed parallel processor. Lots and lots of tiles, I call them. Each tile has a processor. The processor may have multiple threads, and the processor also has some memory. There is no other memory in the system. There are no shared resources. Sharing things between 3 or 4 people is kind of all right. Sharing things, anything, sharing logic, sharing memory, sharing anything between thousands and thousands of processors is always going to be inefficient. They need to talk to each other, so you need some sort of communications fabric, but that communications fabric should be stateless. Ideally, it should also be deterministic, so the compiler can do a decent job of this compiling of patterns of graphs. The threads on the processor, they only need to hide what happens locally. So they need to hide things like branch latencies and memory access latencies and maybe complex floating point operations. But that suggests a handful of threads, not the thousands of threads that you currently see deployed to try and hide external memory access latencies. So here we are today, 2018. There are 2 plans. There is the GPU plan, in which you have a large logic-only die, pretty much. There's some memory on a GPU, but not very much. Mostly logic. You can't actually power you can't power all of the die area on a modern GPU. This is one reason why modern GPUs target multiple markets. They put down different hardware for different markets, because they know that you can't turn all the hardware on. So otherwise there wouldn't really be anything put on the die. So a GPU is designed to have 64-bit floating point for HPC, no use to graphics, no use to machine learning. It has lots of 32-bit floating point, obviously that's graphics mainstream. Not much use to machine learning, we now know, a little bit perhaps. And now it's got things called tensor cores, 16-bit floats, 32-bit accumulation, that's what machine learning needs. No use to HPC, no use to graphics. So it's a multi-purpose pool of logic, and then we attach that to a bunch of external memory, DRAMs, what's called HBM2s, high bandwidth memory generation 2, on a silicon interposer, so a rather expensive electromechanical construction. 6,500 wires connect the memory die to the processor die. And you can get, now you can get, NVIDIA have just announced 32 gigabyte versions of Volta. Haven't seen any yet, but they've announced them. That's about 900 gigabytes per second. So lots of, quite a lot of memory, quite good bandwidth. Contrast that with what I've just been talking about, which is what GraphCore are doing. We actually build our chips to use about half of the same amount of power as the GPU. So that GPU subsystem there is about a 300-watt board. Actually, the clump of gear that you see there gets about 250 watts, because the other 50 watts is used in voltage regulator supplies. So for the same power, same total power to the module, we put down 2 lower power density chips. They're lower power density because they're mostly memory. And they are distributed multiprocessors, as I have described. We bolt the 2 together with as many high-speed links as we can possibly get along one pair of edges. And we end up with a much smaller memory, but it's all on the chip. About 600 megabytes. It's interesting. I've got a countdown clock here and it's running about a third of normal speed. I better use my watch. About 600 megabytes, but we can access that at 0 latency at spectacular bandwidth, effectively infinite bandwidth. And you can power a similar amount of logic in both cases. So the key question is, can you get more performance from the guy on the right than you can from the guy on the left for the same power budget? Obviously the answer is yes, otherwise I wouldn't be here. The other difference is there are many, many smaller processors on the one on the right, and there are fewer larger processors on the one on the left. So there's a difference in granularity. And I think that's going to suit, the more we go to the interesting mode of parallelism being graphs, the more that's going to be appropriate. Because graphs are characterized by sparsity. Sparsity wants fine-grained parallelism. Here it is in a bit more detail. So these chips are about 800 square mil, they're about as big as you can make. They each have about 1,200 processors, so you've got about 2,400 processors on a pair of die on one PCI Express card at 300 watts. And in total, we have something over 200 teraflops available. You'd be lucky if you can get all of it, as I previously pointed out. And there's not much else on the die, apart from a communication fabric in the middle that allows the processor tiles to talk to each other at very high speed, spectacularly high speed. So every one of those processor tiles can talk to every other one at the full speed of the processor on a bus 32 bits wide, with no collisions, no delays, no blocking, nothing. It's the sort of thing you can only do on silicon. You can't do that on a board or in wires in a data center. About 8 terabytes per second on each of those two spines, actually. So it's effectively perfect interconnect on the chip. It's not perfect between the chips. That's something that we'll constantly try to improve, but that's physics. And then the only other thing really on the chip are very high-speed links, which we can use to connect together groups of these pairs. So we can build bigger clusters of these chips, get them all to cooperate. The operating mode of the chip is interesting. It's an old idea, but I think it's the first time it's been built in silicon. It's what's called bulk synchronous parallel. This is the only paradigm for very highly parallel computing in which you cannot write a program which has a concurrency hazard. And that's because it's bulk synchronized. So what that means is there's a synchronization event in which all tiles participate and they all agree what time of day it is. As soon as that synchronization event has occurred, everyone is free to start communicating with everyone else. And communication is just memory-to-memory transfers of data. There's no computation going on at this point. It's purely transfer of data. Because the interconnect is fully deterministic and because the communication patterns were compiled, they can be very efficient. We've had the luxury of being able to spend a long time getting that schedule right. As soon as a tile, individual tiles, have sent all of the values they need to send to other tiles and received all the values they need to receive from other tiles, then they can independently start computing. But they only compute on stuff that's local to the tile. And then that whole sequence of 3 steps is called a BSP step, or sometimes a super step. And that repeats again and again. And there are some nuances to do with talking to the outside world and talking to other chips over non-deterministic interconnect. But the basic idea is that instead of overlapping communication and compute, you serialize them, and each time you do a pair of those things, you synchronize the entire chip. No live locks, no deadlocks, no races, whatever your parallelism. Really easy to understand. Whether GraphCore succeeds in this business or not, I advocate the use of this idiom for parallelism for whatever does succeed. Why is it a good idea to serialize communication and compute? It sounds inefficient. So it's inefficient if you're not power limited, and it's efficient if you are power limited. And if you look at the top row, this is what we used to do. When we were designing a chip, you would allocate some of your power to computation and some to communication. And if the workload that you actually had to run didn't have that mixture, in this case it's limited by communication, then what happened was your program still took the same amount of time to run, but you burnt less power. Now that's not what we want now. We want to burn all the power we've got all the time. If you serialize, then instead of saving power, you save time. Because the compute only takes as long as it needs to, and the communication only takes as long as it needs to. The challenge you have is that you have to load balance your machine such that the synchronization events, which are vertical bars on that lower line there, are straight. You don't waste too much time. Now, if you've got a deterministic interconnect and you can compile your communication, then you can do that. Here's a real trace. This is from the Colossus machine training ResNet 50. This is just a few BSP steps. I've color-coded the synchronization event purple. Communication is yellow, and blue is compute. And the pale blue is waiting for everyone else before you can synchronize. So pale blue is wasted, except in the case I've highlighted at the top, where everyone well, where some tiles are unused, then we can adapt the clocks. But if all tiles are being used and some are waiting for sync and some are not, then you waste some time. And the vertical axis here is 1,200 tiles, basically, just sorted so that the graph looks nice. And if you, this is the whole of one forward and backward pass of backprop on that network. Obviously, I've chopped it up to lay it out in a square. It's actually one very long line. And you can probably optically assess the efficiency of the system there. All the light blue is wasted. So we're wasting maybe 10, 20% of the potential performance. That's as good a job as we can do for load balancing this particular network. Otherwise, it's looking quite good. There's opportunities for us to improve, obviously. Right, so Colossus, our machine, the IPUs, distributed machines of this type, they integrate enough memory to hold a big model on the chip. Or if that doesn't fit, then at least cluster a few chips together and hold a big model on a small cluster of chips. Now in GPU terms, that's what they call fusing kernels. So you never have to go off chip to refetch data. You never have to store the result of one computation off chip and then fetch it back to continue. Everything's always on the chip. This means we can access all the data we need all the time at essentially zero cost. Now that's fantastic for anything that's memory bottlenecked, and things like RNNs and wavenets and stuff like that are famously memory bottlenecked. If you don't believe it, we've got some benchmarks on our website, graphcore.ai, that show our system running 200 times faster than Volta for those things. But what about stuff that GPUs are really good at, like CNNs with big batches? How do we deal with that? Because they require a lot of memory, especially with batch normalization over big batches. So here's a little preview of a paper which will be posted to archive later this week. We've just uploaded the final version today, I think. We have, so Dominic and Carlo are two members of our research team in Bristol. And this is just a bit of empirical research in which we have explored the question of what is the optimum batch size and learning rate for training CNNs. They've looked at various different structures of CNN and they've swept learning rate and batch size and tried various things, batch normalization, warm-up strategies, data augmentation, etc. I will just point out that we use a slightly different definition of learning rate here, so that for all learning rates in the graphs I'm about to show you, the compute load is the same. So in other words, learning rate doesn't mean anything about how fast the network trains. It's just a question of how big a step you take each time you do an SGD iteration. And all we've done here, we've actually gone back to what people used to do more than 5 years ago, which is for a batch, update the weights by the sum of all of the gradient deltas rather than by their average. It just makes the maths fall out easier. It's exactly identical, but that's the way the graphs are calibrated. So all runs do the same amount of compute. And I'm going to show you some examples for ESNet32 on CFAR 100, but there are many others in the paper, which you'll soon be able to see. So here we are. We plot test accuracy of the network against, on the left, batch size, and on the right, base learning rate. So it's a three-dimensional space, if you like, and here are two-dimensional views of it. You can see very clearly that there's an optimum learning rate, and there's also an optimum batch size. And the optimum batch size is really rather small. In this case, about 8. You will get the best models with a batch size of about 8. Not only that, actually, but if you look at the learning rate curves on the right, small batches give you reliable, robust convergence over a broad range of learning rates. So you don't have to get that hyperparameter right. Whereas big batches become more and more sensitive to getting the right learning rate. Now, there's been a lot of papers recently published about trying to push ever larger batch sizes because that's what GPUs require for efficiency, and TPUs the same. Obviously, we're looking in the other direction because we're looking at machines that require small batch sizes, and we're asking the question, can we get better results? It used to be broadly accepted that small batch sizes gave better results. People have kind of forgotten that, so we're reasserting that point. Various strategies have been proposed for improving the behaviour with large batch sizes, and one of the best known ones is warm-up, proposed by Goyal last year. And so we've applied that to the same case here, and you can see that it does actually, if I flip between those two, it does actually improve the story for big batches, but doesn't level it off. So small batches still best, batch size somewhere between 4 and 16. So SGD with small batches does yield better models. And convergence is also less sensitive to the choice of learning rate, so you don't have to be quite so careful. Machines that are very efficient, if you can build a machine that's very efficient for small batches, then even if you want to use big batches, you get to parallelize over more machines, more chips. And the IPU is a machine that's efficient with small batches. So if you really wanted to use big batches, just parallelize over more chips. And obviously you can parallelize over more chips than you could with a machine that required a big batch per chip. It does mean that the clustering of chips has to be efficient for the all reduced type functions between chips for shared batch norm and also for the weight updates in SGD. Now, as well as that, so small batches, good idea, that suits our machine. There are other things we need to do, other types of algorithms that we need to emphasize to get these memory-centric machines to outperform, in other words, to release their potential. I've just put down a couple of examples. One is to trade recomputation for memory. In other words, whenever you think of storing something, assess the expense of recomputing it instead. Storing and retrieving off-chip is very, very energy hungry. It's often cheaper to recompute something on-chip than it is to store it off-chip. And then the last one is reversible models. There's some very interesting work started to emerge last year about networks that do not require activations on the forward path to be stored, because actually they're dynamically recomputed automatically when you do the backpropagation. So their memory footprint is tiny. Here's an example of trading recomputation for memory. So this is DenseNet 201 with a batch size of 16. And what we've done is we've just observed how TensorFlow allocates memory as it does forward, backward pass, and then a weight update. So the x-axis is just allocations in time order. It's not actually time, it's just a sequence of memory allocations. And you can see the amount of memory allocated goes up as it stores all the activations on the forward pass, and then as it consumes them all on the backward path, it goes back down again. Now, if instead of storing all those activations, we store some snapshots. So in this, we have a very simple strategy. We store one activation for each residue block. And then for the activations we haven't stored, we recompute them from the nearest one that we have stored. You do a little bit more work, about 25% in this case. The worst case is you redo all of your forward pass compute. So your worst case really in terms of dot products is a third of the total work. In this case, it happens to fall out about 25% of the total work, and we save a factor of 5 in memory. So this is the sort of thing that you need to do to get a small memory machine to fly. And obviously you can hide that sort of stuff in libraries. It doesn't need to be very explicit. You can do that for your programmer. Here's the reversible networks that I mentioned. There are actually several of these now. But you can arrange your residue system and your convolutional mappings such that you never need to store an activation value. So you throw them all away on the way forwards, and then you compute a cost function, and as you go backwards, you don't need those ones you threw away. So the memory footprint of a reversible net is completely dominated by the weights. And that, of course, is what we'd like. We'd like to sell chips that will hold a network of, 1 billion weights. Here's a 1 billion weight chip. And it shouldn't matter how much dynamic stuff gets computed, because that should be a small part of the memory. It shouldn't matter how much space is required for the programs to run, etc. I'd love to be able to sell a 1 billion weight chip, or a 100 million weight chip, whatever you want. So to recap, finally, now I've got the watch. So the timer actually says I've taken just under 20 minutes, which obviously is a lie. To recap, throughput processors will be increasingly power limited. That is just physics. There is no alternative until someone invents something totally different, like quantum computers. They will come, but not for a while. So therefore, if they're power limited, they must become mostly memory. So whether we've got the right idea or whatever, you can form your own judgment, but chips will become mostly memory, processor chips. We've already got to the point where we can embed pretty big models on a chip. In other words, there's enough memory to do this sort of thing. If a big model doesn't fit on one chip, then a small cluster of chips will do it. And this large batch thing is a bogeyman. Not only do you not need large batches, actually they are harmful. You will get better results, you'll get more stable learning with small batches. And that'll give you a small memory footprint, be more power efficient as well. Efficient massively parallel processors need not to be surprised by communication traffic. In other words, they need that to be compiled. It's part of the program. In a massively parallel machine, maybe that is the most important part of the program. Maybe it's more important than the compute that happens at the vertices of the graphs. So that means that program graphs must be pseudo-static. There are various initiatives to try and take some of the graph frameworks and make them more dynamic in terms of dynamic graph structure. That's probably ill-motivated. And finally, BSP, bulk synchronous parallel, I think is a beautifully simple, concurrency safe, and power efficient paradigm for massively parallel computing, which includes machine intelligence. Okay, finally, how do you get to try out an IPU? If I had £1 for everyone that wanted to try out an IPU, I wouldn't need to go to work. Our priority commercially is, rather than try and feed all the people who want one, to feed a few people who have very big cloud infrastructure with them so that everyone can then access them. We are also prioritising a small number of research groups who are real thought leaders. So at the moment we're working exclusively with those two classes of customers, and very soon through those two mechanisms you will see IPUs emerge. Locally, just to plug a bit of London here, there is an entity called the Machine Intelligence Garage in the Digital Catapult up near King's Cross. They have set up to make different types of machine available to startups, UK startups, to try out. Obviously, we are going to give them some machines. Don't beat them up yet. We haven't given them one yet, but we very soon will. So if you're a UK startup and you want to try some stuff out for free, then that's another way of doing it in the very near future. And we have two representatives of the MI Garage here, so you can go and ask him when you can get one. Okay, that's it. Thank you. Give some more round.